Welcome to Algebra 2, Unit 7, Lesson 14, Practice Problems. This lesson has one vocabulary term, and that is treatment. In an experiment where you are comparing two groups, one of which is being given a treatment, and the other of which is the control group without any treatment, the treatment is the value of the variable that is changed for the treatment group. If you have any questions about the vocabulary term treatment, please ask for clarification now before we begin on the practice problems. In the first practice problem on page 1, it says Lynn is working on a science experiment. She wants to determine whether salt water boils faster than fresh water. She collects 10 samples of 100 milliliters of salt water and 10 samples of 100 milliliters of fresh water. She places each sample in a beaker on a hot plate. She then records the time it takes to boil for each group and finds that the difference in mean times for the group is 24 seconds. Lynn writes a computer program to recombine all the data into all 184,756 possible different groupings and finds that 4,008 of the different groupings have a difference in means of at least 24. This should say seconds, not grams. Is there enough evidence for Lynn to conclude that the difference in means is due to the addition of salt to the water? Explain or show your reasoning. As we begin to solve this, we want to find out what percentage of the time we actually found differences that were just as large or larger, and then think about that as a percentage of the whole. So what we're going to do is we're going to take the 4,008 where it did have just as large or a larger difference than our original, and we're going to divide that by all of the possible different groupings that were tested. 184,756. And this is a proportion of 0.022. Or, if we want it in percentage, that is 2.2%. If you can only get a difference as large as your experimental difference or larger 2.2% of the time when you randomly simulate the combinations, then this means it is likely your treatment. So, yes, it is likely the addition of salt to the water because it only happened by chance 2.2% of the time. And as a general rule, anything 5% or less is going to be considered low. Anything more than 5%, we could say maybe it was chance. But if it's less than 5%, it likely wasn't chance. It likely was the addition of the treatment. If you have any questions about how to analyze a practice problem such as this to make a determination between treatment or chance, please ask for further clarification so that you are prepared before we move on to the next practice problem. On page 2, this one says technology required. So what you're going to do is you are going to do a Google search for a normal distribution calculator. And then you can pick any of them that come up. I'll take the first one. And this is what we'll use on some of these questions. It says researchers are tagging sharks using 2 different types of devices and want to know if the devices affect the heart rate of the sharks. They tag one group of 8 sharks with a small device that collects a small amount of data, and they tag another group of 8 sharks with a larger device that collects a larger amount of data. They then measure the mean heart rate of the different groups and find that the difference in means is 2.5 beats per minute. Researchers run 1,000 simulations, regrouping the data into 2 groups at random, and record the differences in means for the groups in each simulation. The histogram shows the differences in means from the simulations. They determine that the mean of the differences of means from the simulations is 0.28 grams, and the standard deviation for the differences of means from the simulations is 1.124 grams. So these should not be grams, these should say beats per minute. So the first question asks, what features of the distribution in the histogram let you know that modeling with a normal distribution is reasonable? And there's 2 features that tell us this. And that is it's bell-shaped, and symmetrical. Remember that if it does not meet these two features, then you cannot use a normal distribution curve. Question 2. Model the simulations using a normal distribution with a mean of 0.028 and a standard deviation of 1.124. What is the area under this normal curve that is more extreme than 2.5? So this is where we're going to use that calculator that I had you find online. The first thing it's going to ask for is the mean, and we're going to enter 0.028. The next thing it's going to ask for is the standard deviation, and we're going to input 1.124. And the last thing it's looking for is what area we're looking for. And we want more than 2.5. So we're going to say above 2.5. And now we see that our area probability is this little gray area on the right side of this curve, and that probability is 0.0139. Number 3, based on the area under the normal curve, is there evidence that the original difference in means is likely due to the type of device used to tag the sharks? Explain your reasoning. Well, 0.0139 is 1.39%. So if we can only replicate differences as large or larger than the experiment by randomization, then it is unlikely due to chance. So, yes, it's likely the device because differences that large or larger only occurred 1.39% when randomized. Again, anything less than 5%, it is unlikely that it was random chance. In this case, 1.39% random chance means it was likely the device that caused the differences we saw. If you have any questions about how to use this information or the online calculator to decide whether it is a treatment causing the differences or random chance causing the differences, please ask for clarification now before we move on to the next practice problem. On page 3, our last practice problem says a human resources experiment about job satisfaction takes 10 subjects and divides them into 2 groups using a random process. The control group contains 5 subjects and the treatment group contains 5 subjects. Each group is asked to rate their job satisfaction on a scale from 1 to 10. The control group results in the data 3, 7, 8, 10, and 10. The treatment group results in the data 5, 6, 7, 7, and 9. Statisticians run 100 simulations, regrouping the data into 2 groups at random and record the differences in means for the groups in each simulation. The histogram shows the differences in means from the simulation. So question 1 asks, what is the difference in means between the 2 groups? So for number 1, in the control group, we have 3 plus 7 plus 8 plus 10 plus 10, and we're going to divide by 5. 10 plus 10 is 20, plus 8 is 28, plus 7 is 35, plus 3 is 38, and 38 divided by 5 is 7.6. The treatment group is 5 plus 6 plus 7 plus 7 plus 9 divided by 5. 9 plus 7 is 16, plus 7 is 23, plus 6 is 29, plus 5 is 34. And 34 divided by 5 is 6.8. So the difference in means between the group is plus or minus 0.8. Number 2 asks what proportion of the difference in means from the simulation have a difference at least as great as the difference in means between the control and treatment groups. So, below negative 0.8, we have 4, 7, 3, 2, 2, and 1. 4 plus 7 is 11, plus 13 is plus 3 is 14, plus 2 is 16, plus 2 is 18, plus 1 is 19. So it occurs 19 times on this end. Now above 0.8, we have 10, 5, 3, 6, and 3. 10 plus 5 is 15, plus 3 is 18, plus 6 is 24, plus 3 is 27. So 27 plus 19 is 46. So the proportion is 46 out of 100, or 46%. And number 3, is there enough evidence to support a claim that the original difference in means is likely due to the treatment? And in this case, no. Because differences as large or larger occurred 46% of the time from chance. So in this case, it was almost just as likely that we would see those results by random chance as we would see those results from the actual treatment. So in this case, it is not likely that the treatment had anything to do with the numbers that we saw. If you have any questions about how to compare these mean differences between the experimental results and randomization results, and then determine whether it was likely the treatment or whether it was just as likely to be random chance, please ask for clarification before we move on to lesson 15.